Hey everyone, and welcome back for another deep dive.
It's great to be back.
Today we're going to be talking all about surface chemistry.
Sounds exciting.
It is, actually.
Yeah.
And I think a lot of people would hear that and think, oh, chemistry, that's kind of boring.
Right.
But it's really not.
No.
It's actually incredibly fascinating and the foundation of so many technologies that we just take for granted today.
Absolutely.
And the best way to learn about a topic is always to go straight to the source.
Yeah, for sure.
So we're going to be looking at a Nobel Lecture
Wow.
from 1932
Okay.
by Irving Langmuir,
Irving Langmuir, a legend.
who won the Nobel Prize for his work in surface chemistry.
Huge.
So this is going to be a good one, I think.
I think so, yeah.
And it's presented by Professor Pushpito Ghosh
Okay.
from the Institute of Chemical Technology in Mumbai.
Right. So what did he revolutionize?
The way we understand how molecules behave on surfaces.
Surfaces, huh? Seems pretty basic.
You'd think so, right?
Yeah, what's so complicated about that?
Well, before Langmuir, scientists were kind of in the dark.
What did scientists know before Langmuir came along?
Well, they had a concept of adsorption.
Adsorption, that rings a bell.
It's when molecules stick to surfaces. But their understanding was pretty basic back then.
So they knew molecules could stick, but what else?
They didn't really picture them forming a distinct layer on the surface.
Interesting. What did they think happened?
They often compared it to Earth's gravity holding onto the atmosphere. They imagined a gradual decrease in concentration as you move away from the surface.
So no clear boundary, just a sort of fading out of molecules.
Right. And that's where Langmuir's work really changed things.
So he was the one who figured out these layers actually exist.
He was. But to understand how he did it, we need to talk about his unique advantage.
Okay, what was his secret weapon?
Well, he worked at General Electric.
GE.
They were heavily invested in improving incandescent light bulbs, for one.
Makes sense. Light bulbs were a pretty big deal back then.
Absolutely. And they were also developing thermionic emission devices.
Thermionic emission. Now that's a mouthful.
I know, right? Think of it like this.
Okay, I'm listening.
It's when electrons escape from a heated surface. So GE was developing things like rectifiers.
Rectifiers, what are those?
They're crucial for controlling electric current.
Ah, so kind of like electrical traffic cops.
I like that. They direct the flow of electricity.
Okay, so G was working on light bulbs and these rectifiers. What does that have to do with Langmuir and his surfaces?
Well, to develop these devices, GE needed really advanced vacuum technology.
Vacuum technology, as in sucking all the air out.
Pretty much. But they needed vacuums that were far more advanced than what most labs had at the time. And that's where Langmuir comes in.
Okay, so he had access to this fancy vacuum equipment.
Exactly. It allowed him to do experiments with incredible precision.
I'm sensing that precision is going to be key here.
You're right. Langmuir could measure pressure changes that were unbelievably tiny.
So he's got his super vacuum and his molecule tracking abilities. What's the first mystery he tackles?
Hydrogen gas.
Hydrogen. Seems pretty basic.
It is. But it led to some surprising discoveries.
Okay, I'm all ears. What did he do with the hydrogen?
He introduced it into an evacuated bulb.
Another one of those light bulbs?
Yep. But this one had a heated tungsten filament inside.
Ah, like the filament that makes the light bulb glow.
Exactly. He wanted to see what would happen when the hydrogen met the hot filament.
I'm guessing it didn't just sit there politely.
You guessed right. Langmuir observed something interesting.
Tell me.
The hydrogen started disappearing from the gas phase.
But where did it go?
That's what Langmuir wanted to find out. Scientists called this phenomenon cleaning up. But the real breakthrough came when he did something unexpected.
What did he do?
He added a second filament to the bulb.
Wait, why a second filament? One wasn't enough.
It was a clever move. He wanted to test a hypothesis.
Oh, I love a good scientific hypothesis. What was his idea?
He thought that if the hydrogen was being absorbed by the filament itself, then adding a second filament should double the cleanup rate.
Makes sense.
But that's not what happened at all.
Really? So the hydrogen wasn't going into the filament?
Nope. To Langmuir's surprise, the cleanup rate stayed exactly the same.
That's strange. So if it wasn't the filament, where was the hydrogen going?
That was the million-dollar question. The only other option was
Don't keep me in suspense.
the glass walls of the bulb.
The glass walls? Really? That's unexpected.
It was a real puzzle. But Langmuir, being the brilliant scientist he was, started digging deeper.
I bet he didn't give up easily.
Oh, absolutely not. He realized that the heated filament was doing something to those hydrogen molecules.
Breaking them apart, maybe.
Exactly. It was splitting those hydrogen molecules, which are two hydrogen atoms paired up.
Okay, so it's splitting the pairs. What happens then?
It creates single hydrogen atoms, which scientists call radicals.
Radicals. Those sound a little dangerous.
They are highly reactive. They can't exist stably on their own in the gas phase.
So they're desperately looking for a partner.
Exactly. They need to react with something to become stable.
And in this case, they found their match on the glass walls.
You got it. They attach themselves to the glass surface.
Ah, so that's how the hydrogen disappeared. It was bonding with the glass.
Scientists call that process adsorption.
Okay, so the filament was like a molecular matchmaker.
I love that analogy. It broke up the hydrogen couples and sent them off to find stability on the glass walls.
Brilliant. But I bet Langmuir didn't stop there. He seems like a measure everything kind of guy.
Oh, you're absolutely right. He wanted to understand this whole adsorption thing quantitatively.
Makes sense. For scientists, seeing is just the first step, right?
Exactly. Measuring is where the real understanding begins.
So what did he measure?
He carefully calculated the maximum amount of hydrogen that could be adsorbed.
To figure out how much hydrogen the glass could hold.
Precisely. And here's where it gets really fascinating.
I'm on the edge of my seat.
Using the known diameter of a hydrogen atom.
Okay, so he knew how big a single hydrogen atom was.
He calculated that this maximum amount of hydrogen
The amount that stuck to the glass.
corresponded perfectly to a single layer of hydrogen atoms covering the entire surface.
Wait, so like a perfectly tiled floor but with hydrogen atoms?
Exactly. He called it a monolayer.
A monolayer. Like
Yeah.
a single layer of molecules all lined up neatly.
Precisely. It was a revolutionary concept.
So he was the first to prove that these layers actually exist.
He was. It completely changed our understanding of how surfaces work at the most fundamental level.
It's amazing how something as simple as observing hydrogen in a light bulb could lead to such a groundbreaking discovery.
It really is. And this was just the beginning of Langmuir's incredible journey into the world of surfaces. He also observed that these adsorbed hydrogen atoms weren't just sitting there passively.
Oh, what were they up to?
They were surprisingly stable, even at room temperature.
So they weren't eager to pair back up into hydrogen molecules.
Nope, they were quite content hanging out on the glass surface.
Interesting. And I bet there's more to the story.
You bet there is. But before we delve into that, we need to talk about another key player in this molecular drama. Oxygen. Oxygen had a rather dramatic role to play in Langmuir's research. We left Langmuir carefully observing all that hydrogen
And how it was behaving on the surface.
of his glass bulb.
It was fascinating stuff.
Definitely. But we can't forget the big picture here.
Yeah, he was trying to...
Langmuir was working at GE,
Yeah.
and they were trying to,
Make better light bulbs.
exactly, improve those early light bulbs.
Those other devices.
Right, the thermionic emitters.
They relied on electrons, right?
Exactly. And oxygen
Oxygen.
turned out to be a bit of a problem.
Oh, how so?
Well, think about it.
Okay.
At the heart of these devices, you have the tungsten filament.
Right, the little wire inside.
And tungsten, when it's heated,
The really high temperatures.
it reacts with oxygen.
Ah, so the oxygen is messing with the filament.
It is above 2200 Kelvin.
That's really hot.
It is. The tungsten reacts quickly with oxygen,
Okay.
and they form tungsten oxide.
Tungsten oxide, is that a bad thing?
Well, at those high temperatures,
Like 2200 Kelvin.
the tungsten oxide evaporates.
It just disappears.
It leaves the surface.
Oh, interesting.
So the filament's actually self-cleaning at those temperatures.
So problem solved?
You'd think so, right?
What? Well,
There's a but. At lower temperatures,
hmm.
below 1800 Kelvin,
Still pretty hot.
it is. But at those temperatures, things get a bit more tricky.
How so?
Even tiny amounts of oxygen.
We're talking like,
Really low pressures, almost a vacuum.
okay.
They would drastically reduce the electron emission from the filament.
Ah, so that's the problem.
It is. Remember,
Yeah.
these devices relied on that steady stream of electrons.
For the thermionic emission,
Exactly. And any disruption
even from a little bit of oxygen.
could really mess things up.
So like tiny little saboteurs messing with the whole system.
That's a great way to put it. These trace amounts of oxygen,
They were causing big problems.
they were. Langmuir knew something was going on,
On the surface of the filament,
even though it looked clean.
so the oxygen was hiding somehow.
He suspected it was forming a film, a tightly bound film.
A film you couldn't even see.
Exactly. And to investigate this,
Of course.
he did what he did best.
Measured everything.
You know it. He measured how long it took
Took for what?
for the oxygen to desorb,
Disorb.
to detach from the surface.
Ah, okay, got it.
And he did this at different temperatures.
To see how temperature affected things?
Yeah, exactly.
I can only imagine how difficult those measurements must have been.
Oh, they were incredibly precise.
He was really pushing the limits of what was possible.
He was. And what he found was pretty amazing.
Okay, tell me.
At the typical operating temperature,
For those devices.
around 1500 Kelvin,
Okay.
it would take
How long?
3 years
3 years? For what?
for half of the oxygen film to evaporate.
Seriously? So those oxygen atoms were really stuck on there.
They were clinging on for dear life, which explains why.
Right, even those tiny amounts were causing so many problems.
Exactly. They were so persistent because they were basically glued to the surface.
Wow. So what did Langmuir make of all this?
Well, he realized that the oxygen, just like the hydrogen,
It was forming a monolayer.
exactly, a single layer of oxygen atoms on the tungsten.
But unlike the hydrogen,
This monolayer was causing trouble.
by blocking those electrons.
Precisely. It was preventing the filament from releasing electrons efficiently.
And this is where he came up with that idea of catalytic poisoning, right?
You got it. This is the first time
The first time what?
that someone experimentally demonstrated this concept.
Of catalytic poisoning.
Exactly. It was a huge contribution.
To our understanding of how surfaces work.
Exactly. It showed that even tiny amounts of a substance,
If they stick to the surface.
they can dramatically reduce the effectiveness of a catalyst,
And in this case, the catalyst was...
the tungsten filament,
It's amazing how something so small
like a single layer of oxygen atoms.
can have such a big impact.
It is, and it really highlights
I
the
see.
importance of surfaces in chemical reactions.
They're not just passive bystanders, are they?
Not at all. They're active players in the whole process.
So what did Langmuir do next?
Well, he had this oxygen-covered filament,
With those stubborn oxygen atoms clinging to it.
but he decided to introduce hydrogen.
Hydrogen, back into the mix.
Exactly. He wanted to see how those two gases
How they would interact.
on that tungsten surface.
Ooh, that sounds like a recipe for some interesting chemistry.
It was. But at first,
What happened?
it seemed like the hydrogen had no effect at all.
Really? So the oxygen just ignored it?
It pretty much did. The oxygen kept being absorbed.
As if the hydrogen wasn't even there.
Exactly. It was like watching a one-sided competition.
So I'm guessing Langmuir didn't just give up.
Oh, absolutely not. He was a persistent guy.
Thank goodness for that. What happened?
He kept observing, patiently waiting
Yeah.
after a long delay.
How long?
Well, it's hard to say exactly, but a significant delay.
Okay,
He observed something dramatic,
tell me.
a sudden drop in pressure.
The pressure in the bulb,
Yep, and it meant
it meant what?
the hydrogen was finally being absorbed.
So it was just biding its time.
That's a great way to put it. But here's the really interesting part.
Okay.
It was being absorbed at the same rate
The same rate as what?
as if there was no oxygen present at all.
Wow. So the hydrogen was eventually able to overcome those stubborn oxygen atoms.
It was. But how?
Yeah, how did it manage that?
Well, Langmuir realized that even at 1500 Kelvin,
Still pretty hot.
those oxygen atoms weren't permanently stuck.
They were moving around.
Every now and then, a few would detach from the surface.
So they weren't completely immovable.
Exactly. And as soon as a spot opened up,
What happened?
a hydrogen molecule would swoop in.
Like it was waiting for its chance.
Exactly. It was split into its radicals
Those highly reactive single atoms.
and react with the neighboring oxygen.
The form.
Water.
Water inside the light bulb.
Yep. And that water would then evaporate.
Leaving behind a fresh spot for more hydrogen.
Precisely. It was like a chain reaction.
A domino effect.
Exactly. Triggered by those few hydrogen molecules.
That managed to sneak onto the surface.
It's amazing, right?
It is. So even though those oxygen atoms were holding on tight,
The hydrogen eventually found a way to outmaneuver them.
it's a classic tale of persistence and strategy. And of course,
It all comes back to Langmuir's amazing ability to measure.
those tiny pressure changes.
Without that precision.
He might have missed this whole interaction.
Absolutely. It was a key insight into how hydrogen and oxygen,
Behave on that tungsten surface.
and it had big implications.
Those light bulbs and other devices.
Exactly. It helped them understand how to control those pesky impurities.
That were messing with their performance.
But it's important to remember,
What's that?
all of this was happening.
In those pristine, evacuated bulbs.
Right. A very controlled environment.
So the question is,
What happens in the real world?
where things are a lot messier.
Exactly. It's easy to get caught up.
In the elegance of these experiments
But the real world.
is a whole different ballgame.
All right, so we've been exploring Langmuir's meticulous work.
In those pristine, evacuated bulbs.
Yeah, a very idealized environment.
Definitely. It was all about those clean surfaces.
And he made some amazing discoveries
About how molecules behave.
on those surfaces.
It's the real world.
It's a whole different story, right?
It's those surfaces we encounter every day.
Like what?
The rust on a car. The grime on a city building.
Or even that thin film that builds up on your teeth.
Exactly. They're constantly interacting with a chaotic mix of stuff.
From the air, water.
Everything.
Seems like a nightmare to try to understand all that.
It's definitely more complex.
Yeah.
But Langmuir's work gives us that foundation.
So we're not starting from scratch.
Exactly. We have that baseline understanding
Of how molecules behave on those ideal surfaces.
Right. And from there,
We can start to build up,
add in those real-world complexities,
piece by piece,
develop more sophisticated models
design better experiments.
that reflect those messy environments
It's like we have the blueprint.
from Langmuir's research
And now we're figuring out how to build the real thing.
in the real world
Exactly. And one area where this is super important.
is catalysis,
Right. Catalysts speed up chemical reactions.
without being consumed themselves.
Essential for so many things.
Countless industrial processes.
And it all comes back to surfaces, right?
Absolutely. That's where catalysts do their work.
They provide the stage.
For those molecular interactions,
And Langmuir showed us
how those interactions on a surface.
really change how molecules react.
So when we're designing catalysts
We're trying to choreograph those interactions.
to get the reactions we want,
and suppress the ones we don't.
exactly. It's all about controlling those molecular dancers.
But on a crowded dance floor,
Things can get messy.
like those impurities that can contaminate a catalyst,
Exactly. They get in the way.
that's Langmuir's catalytic poisoning again, isn't it?
It is. Those impurities are like party crashers.
Ruining the carefully choreographed dance.
So we need to understand how those poisons work.
To design better catalysts.
Ones that can resist those unwanted guests.
It's amazing to think
Yeah.
that surfaces are so important.
They're not just passive bystanders.
You're active participants in the whole thing.
They're where the action is.
This has been such a fascinating journey.
It has.
It's incredible how Langmuir's work,
Which focused on those simple experiments,
in a vacuum,
has had such a huge impact
on our understanding of the world.
and our ability to solve real-world problems.
It all started with his curiosity about those tungsten filaments.
Who knew those little wires held so many secrets?
It's a great reminder that even the most basic research,
Can lead to amazing breakthroughs.
and next time you flip on a light switch
Or take a medication.
or drive a car,
Think of Langmuir.
his research might be behind it all.
It's a testament to the power of scientific curiosity
Of careful observation.
and that relentless pursuit of understanding.
Thanks for joining us on this deep dive into surface science,
I hope you've enjoyed the journey.
and that you'll never look at a surface the same way again.